Hi everyone, my name is Xu Chen. I am a PhD student at the University of Electronic Science and Technology of China. The paper I will presenting today is titled BASE, Bridging the Gap Between Cost and Latency for Query Optimization. This work is from UESTC and Alibaba Group. In this work, we use machine learning method to train an end-to-end query optimizer with better efficiency and stability. Let's first review the traditional query optimizer. In traditional optimizer, query optimization is performed based on the cost estimation, also known as the cost-based optimization or CBO. The CBO optimizer is tasked to determine the best physical execution plan based on the logical plan tree, including determining the join order and physical operators. Let's see the flow chart. We can see that the input is the logical plan tree, and the CBO outputs the optimal physical plan tree. In the CBO, it is necessary to first estimate the cardinality for each subtree. Using these estimations, along with the calculations involve some magic constants, the total cost of subtree can be estimated. Finally, dynamic programming is used to search for the optimal tree structure and the physical operators to obtain the optimal physical execution plan. It should be noted that these magic constants are usually time unit constants, such as the unit time for the table scan. They are considered as magic because the optimal parameter values cannot be determined accurately. Instead, heuristic estimation or the manual setting of these magic parameters is used. In addition, there are naive assumptions in the cardinality estimations, such as columns are independent of each other. So, all these heuristics make CBO show unsatisfactory performance. Nowadays, we start to use the execution feedbacks to enhance the CBO. With the popularity of machine learning and reinforcement learning, people use reinforcement learning-based models to choose better plans to avoid aforementioned heuristics. In the jargon of reinforcement learning, we call them the learned policy. However, they also suffer from fundamental limitations. Since machine learning models are trained in a data-driven manner, it needs to collect a large amount of execution feedbacks as the training data. Collecting the latency of the execution plans is a time-consuming process, which leads to the slow convergence of the model. Here we summarize the problem mentioned earlier. We know that for the query optimization, it needs to select join ordering and physical operators. It is widely known as the NP-hard problem. Therefore, on the one hand, in traditional optimizer, the cost-based optimization method was developed to approximate the optimal execution plan. However, on the other hand, there is a major drawback in the learning-based query optimizer. That is, obtaining the reward signal is challenging, which makes the training difficult to converge. Here we have three key observations which motivate us to develop our method. The first observation is shown in the first scatter plot. Each point in the scatter plot represents an execution plan. The x-axis represents latency, and the y-axis represents the cost estimated by the PostgreSQL. There is a gap between the estimated and the actual cost, which results in the suboptimality of the execution plans. And the second observation is that collecting the latency signal occupies a significant portion of the training time. In the second observation, we use two different signals, cost and latency, as the reward functions to train an end-to-end learned optimizer in 3 hours. On the one hand, 92% of the time is spent on the query plan execution for latency-based training, and the model is trained for only 226 episodes. On the other hand, 96% of time is used to training the neural networks for cost-based training, and it can be trained for over 88,000 episodes. In the third observation, we conclude that cost-based training has already achieved good performance. In the third observation, we random sample plans from the random policy and the cost-based policy. We find that only a small portion of plans from the plan space outperform than the cost-based policy. In other words, although observation 1 holds, only a small portion of the queries exhibit a large gap between cost and latency in terms of the behavior of their corresponding optimal policies. Based on the advantage of the deep reinforcement learning optimizer, we aim to train an excellent optimizer in the shortest possible time. To balance the effectiveness and the efficiency, Bayes is divided into two stages. The first stage involves using a traditional CBO database optimizer, such as Postgres, as the expert demonstration during training. Typically, cost signals are collected in the millisecond, while latency signals are collected in the seconds. Due to the significant difference in the number of training samples collected within the same time frame, our optimizer can leverage the quick signal collection during the first stage to achieve the fast convergence. However, the ultimate goal has always been to optimize the execution time or latency rather than the estimated cost. Therefore, in the second stage, using an actual execution time, we transfer the optimizer from the first stage to enable it to find the optimal execution plan. The core idea is to address the gap between cost and latency. Based on the training, we need to correct the inaccurate cost signals. Here, I will introduce the system framework of Bayes. There are two stages in total. In the first stage, as shown in the dash box above, the optimizer receives SQL queries from the training dataset on the right. It generates an execution plan tree and submits it to the database for evaluation. The database provides a cost estimate, which is used as the reward signal for reinforcement learning training of the optimizer. In the second stage, as shown in the dash box below, the difference is that we selectively sample training data from the right and selectively sample execution plans. The goal is to quickly identify potential errors in the cost signal. The sampled execution plans are then executed in the database, and the corresponding cost and latency are obtained. We use latency to calibrate the collected erroneous cost signals, and the calibrated cost is then used as the reward signal for continuous training the current optimizer. Here we show the milestone of the pre-training stage. The right figure is relative cost, which is the cost ratio between execution plan generated by model and the plan generated by PostgreSQL. It can be shown that Bayes perform comparably to the traditional optimizer. The bar chart below is the absolute cost, which is the cost value of the execution plan generated by the model. It also shows similar results between the expert optimizer and the learned model. As the figure below shows, next we talk about the policy transfer stage. The figure on the left side shows we input the cost-based reward signal and the query optimization policy converged in the first stage. In the intermediate process, the current policy actively sample execution plans that may have erroneous cost signals. These execution plans are used to calibrate the reward signal denoted by the R5. The calibrated reward signal then trains and improves the current policy. The reward and the policy mutually supervise and enhance each other, ultimately achieve the optimal policy in the latency-based domain. Next, we talk about the details. First, based on the active learning, we actively sample conflicting execution plan pairs that arise from the uncertainty of the current policy. The uncertainty is defined as the entropy of the learned policy. Next, we define the objective function and use gradient updates to calibrate the collective conflicting execution plan pairs. The calibration function is defined as the hinge loss, where we try to inverse the cumulated reward between the conflict pairs. Using the calibrate reward function, we train the current query optimization policy using the reinforcement learning algorithm. Lastly, how does Bayes perform? Here, we use 3 different learned end-to-end query optimizers. The first optimizer is called latency only or LO. It uses latency as the reward function. And also, we use the state-of-the-art learned query optimizers called NEO and BELSA. And also, we apply Bayes to the ML-steered query optimizer called BAO. BAO generates the plans instead of BAO generate plans from the traditional query optimizer. It only tries to tune the knob of a traditional CBO and shows promising results as well. In the first experiment, we show the overall performance. Note that we limited the training time in 10 hours and we use single GPU for training. It can be shown from the table that Bayes outperformed the state-of-the-art method by 11% and outperformed Postgres by 36%. Next, we show training efficiency. The table below shows the time consumption of pre-training stage and the fine-tuning stage of different methods, and it will also report the end-to-end training time on 2 datasets. It can be shown from the table that Bayes saved up to 45% training time compared to the state-of-the-art method. It demonstrates Bayes can achieve better efficiency than the previous methods. Lastly, we apply Bayes to the ML-steered optimizer, BAO. Bayes domain transfer technique can also be applied to the predictive model from a data-rich knowledge base instead of the empty knowledge base. Bayes substantially optimized BAO source code in 2 aspects. First, Bayes initialized the BAO predictive model following our previous initialization method from the cost model. Secondly, Bayes trained the model based on our calibration function training strategy to transfer the knowledge. It can be shown from these 2 figures that Bayes plus BAO has significantly better performance in both at the beginning and also at the ending point of the whole training courses. That's all for the presentation. Thanks for listening.